Cool. 3, 2, 1. Okay, it's recording. Great. Beautiful. All right. Good stuff. All right. We're recording. We're doing good. We're happy. All right. Plot for today. All right. So, as mentioned, I swapped the topics around. The story for today is we're going to start talking linear transforms, one of my favorite topics, and really something you actually have already encountered before you got here, but we're going to get real deep. So, I want you to recall something. In particular, I want you to recall some facts from calculus. God forbid. Okay, so what are the facts from calculus I want you to recall? All right, so the first one that I want you to recall is a couple of facts about how derivatives work. So the first fact about derivatives I want you to recall is the following. So the derivative of a scaled function is the scaled derivative. That's one of the things we learn. All right, what's another thing that we learn? Well, differentiation is a pretty nice operation in terms of not only scaling functions, but also adding functions. So something else that we learn about the derivative is that the derivative of a sum is the sum of the derivatives. Oh, where is it? There it is. Yay. There we go. Right, and both of these fall into a snow clone of the x of the y is the y of the x. Right, the derivative of a scaled function is the scaled derivative. The derivative of a sum is the sum of the derivatives. Right, and in math, there's a lot of things where we phrase things like that. For example, from calculus, still, we know some things about integration. We know that from the fundamental theorem of calculus, differentiation and integration are inverses of each other, essentially. And in particular, then, you could ask, well, we know that the sum and scalars of functions behave nicely with derivatives, and the same is true for integrals. The integral of a scaled function is the scaled integral. The integral of a sum is the sum of the integrals. Right. And note here I wrote indefinite integrals. These can also be definite, and it's the same deal. Good stuff. So again, note here, and again, I'll stress this. Okay, so I'll actually type it out. So again, note the phrasing, right? The way these are set up is the x of the y is the y of the x. Integral of a scaled function is the scaled integral. Integral of a sum of the integrals. Okay. And also recall from this class that we also have encountered this happening where scaled and sums behave nicely. In particular, if I look at a scaled matrix and take its transpose, or if I take a sum of two matrices and look at their transpose, those behave nicely as well. So the transpose of a scaled matrix is the scaled transpose. The transpose of a sum is the sum of the transposes. And again, the x of the y is the y of the x. Okay. Right, and you can find millions of examples across mathematics. And as you go further in your math journey, you're going to encounter a lot of this. Right, and there's a reason you're going to encounter a lot of this, because while this is notationally convenient, this is telling us that there are equation manipulations we can perform. There is something really deep being communicated here. And let's get that deepness phrased in terms of vector spaces, where we've been hanging out, because let's really note something here. If we're thinking about things in terms of vector space language, we're saying that if we look at functions, differentiation respects scaling in a sense, right? doesn't do anything weird to a scalar input. It just says, all right, well, take that scalar out and take the derivative of the actual item. Likewise, the derivative of a sum is the sum of the derivatives. One way we can think of that is differentiation, saying, oh, we got sums, I'll respect that, right? I'll treat sums the way you think they ought to be treated. Right. Right, same thing for the spaces of integrable functions and the set of matrices, right? We have these fundamental operations of scaling and adding, and these operations are treating them accordingly. They're not doing anything crazy to them. Right. So let's capture this behavior that we see in these different settings of functions and matrices and give this a name. And obviously we already know what the name is going to be because I told you what the title of today is. All right, so let's set it up. All right, so if I have two vector spaces and I have a mapping that respects the scaling and adding, we'll call that a linear transform. And now let's get that formally written out here so we're all on board for what it is. Then we'll talk about the ins, the outs, and the what have yous. Then we'll prove a couple of things. And then we will end today with a pretty fun conversation. All right, so what do we mean by a linear transform? Well, we're going to mean a function that does exactly what we've seen before, right? In calculus, we see that derivatives and integrals respect scaling and adding. We have already encountered things that respect scaling and adding for matrices. We will talk about another fun example for Euclidean space in a moment. But let's capture the behavior here. A linear transform is a mapping so that t of alpha x is alpha t of x. You can pull the scaling out. And t of x plus y is equal to t of x plus t of y. So additions break up. Okay. That is what a linear transform is. So it's a function between vector spaces that leaves the structural relations undisturbed. Right? A vector space has scaling and adding associated with it. This mapping says that those scalings and those addings are treated with respect. Okay. And again, it's worth kind of noting here, notationally speaking, we don't really make a distinction, but the scaling here, that's the scaling of the vector space V. This is the scaling with respect to W. Right? Note, I don't have different notation for either of those, but that's really what's going on here. And likewise, this is the summation of V. This is the summation of W. Right? So again, while notationally we're kind of overloading, hopefully you're kind of seeing what's going on. All right. Beautiful. Now, before we move on, some fun words. So generally speaking, we're going to use the word linear transform or linear mapping. But there are two other words with linear that are used that are worth noting. So again, linear transform and linear mapping, we will interchangeably use those. However, there are two linears that are worth noting that have specific meaning. So one is a linear operator. So when somebody says linear operator, they usually mean something very specific. They mean that the codomain of the function is the same thing as the domain. So in other words, it's a linear mapping from a vector space to itself. So it's not transforming from one vector space to another, it's operating on the vector space we are currently looking at. So linear operator is almost universal. They mean the domain and the codomain are the same. Okay. So if somebody says they study operator theory, this is what they're doing. They're studying these. All right, and another one that is worth noting, that occurs frequently is a linear functional. And what is that? A linear functional is when the codomain is the set of scalars. So for us, a linear functional would mean a linear mapping from a vector space to the real numbers. Yeah. And again, we'll talk a little more in a moment here about examples of these. All right. But when somebody says functional, this is what they mean. You're taking a vector space and you're mapping into the set of scalars. Okay. For us, we're focusing on the reals, but of course you can have other sets of scalars as well, such as the complex numbers or the rationals, or whatever your favorite field is. Take the rational numbers and add square root of 2. Go nuts. Okay. All right. Cool. And so, like I said, people that study something called operator theory, they're looking at these. You may have heard this before, but functional analysis is, broadly speaking, infinite dimensional linear algebra, but the fundamental object that you look at are the linear functionals. So if you ever wondered what functional analysis actually entails, this is part of it, and is the sort of namesake for it. Right. I remember when we took real analysis, we were like, oh, it's analysis of real variables. And then complex analysis made sense. Like, oh, it's analysis of complex variables. But functional analysis was like, well, analysis of functions? What is that what we're already doing in real and complex analysis? Yeah. So if you ever wonder where the name comes from, this is where it comes from. All right, cool. All right, so we've already got quite a few examples of linear transforms. All of these ones up here count. All right, but let's get some more examples. Let's get some fun examples. All right, so here's a neat one. Let's go ahead and fix a matrix, M by N. I'm going to create a function using this matrix, N matrix multiplication. So if I now create the function that goes from Rn to Rm, defined as follows, give me a vector of Rn. Well, the matrix is M by N, so I can multiply X by A. And that will output a vector that lives in R3, Rm. It's a 3 that's been turned. Right. This is linear. Indeed, we can quickly prove this. It's not too hard to see why this is true, because again, being linear means that you respect scaling and you respect adding. So if I feed in a scaled input, this says multiply that by the matrix A, but something we know about matrix multiplication, one of the many things we know about matrix multiplication, is that you can pull scalars out, and matrix multiplication is associative, right? So parentheses can be moved as needed. All right, but we can pull the scalars out and note that, hey, you just got A times X, which is what T of X is equal to. So scalars can be pulled out, and likewise we can verify that additions behave. Right, because there you'll have the matrix times the sum, and we know that matrix multiplication distributes over addition. And there we go. So, multiplying a vector by a matrix gives me a linear transformation between Euclidean space. And spoilers, this is the only possible linear transformation that exists between Euclidean space. We'll prove that in a little bit, but for now. Fun question, are there any other linear transforms? No, there's not. All linear transforms between Euclidean space are matrix multiplications. We'll prove that next time. That's not part of today. All right, so hey, that's a pretty fun linear transform. Let's get a functional. And we're going to do a similar setup to create a functional. Fix a vector in Rn. I'm going to create a similar sort of mapping. Then create the mapping from Rn to R as follows. Take our vector and create a real number by computing the dot product with respect to A. Right. So again, remember, dot products are commutative, so you could do A times X or X times A, depending on where you are, you're going to put it one way or the other. I'm going to put it on the left so it mirrors the one we just talked about. Now, it's worth noting that if you want to do the complex version of this with the inner product, you're going to have to be a little careful, because we know that for the inner product, in one of the components you can pull scalars out, but in the other component you cannot. You pull out the conjugate. All right, and if we really want to get off the deep end, we can get into that, but we're not doing that. All right, but anyway, this is linear, and this gives us an example explicitly of a linear functional. And indeed, the proof of this is pretty much the exact same proof we just saw, but with different symbols. But all of the same sort of principles apply. We know something about how dot products behave with respect to these operations. Okay, but to explicitly write it out, we know that if you take a dot product and one of the elements involved is scaled, then the dot product respects the scalar. So indeed, I can pull the scalar out, and we get that scalars are pulled out of my mapping. And likewise, dot products we know distribute over addition. So we're good. Pretty cool. All right. Now, more spoilers. Something that I'm going to make you do on a homework, problem number 5. So like I said, in class we'll prove that the only linear transform from Rn to Rm has to be multiplication by a matrix. Similarly, the only linear mapping from Rn to R has to be dot product with respect to some fixed vector. And once you see how this proof works, then modifying it to get this proof is pretty easy. That is a special case of a theorem called the Riesz representation theorem. So, talk more about that later. Good stuff. All right, great. Well, all right, we got some examples of linear transforms. Pretty exciting. Let's now go ahead and prove some general properties of linear mappings. So, got some examples, and I want to prove some general properties first because, as I've mentioned, when you cook up a math definition, you always want to do two things. You want to find things that satisfy your definition, and you want to find things that don't. Because then it's a definition, right? Because then there's like a boundary to investigate. When do you have this property and when do you not have this property? If you always have the property, right, it's a tautology, who cares, right? And if the thing never works, well, then it's crap. So who cares? All right. So we've established some mappings that are linear. What about mappings that fail to be linear? Well, the easiest way to create nonlinear things is to first note that linear mappings have two pretty restrictive requirements. And that's what we'll start off with today. Okay, all right, and for ease of use with propositions, when I announce that T is a linear mapping, the domain and the codomain are obviously vector spaces, because I can't talk about linear without them. So if I don't explicitly announce that V and W are vector spaces, you know what they are, right? What else does the symbol V mean in this class? All right, I'm just going to be lazy. I don't feel like typing it all out. All right, so if you've got a linear mapping, it turns out that two things have to always be true. Okay, so the first thing that is true is that you have to send the additive identity to the additive identity. All right. And so that's kind of an interesting thing, because again, let's note what vector linear mappings are doing. They're saying that scaling appropriately lines up with scaling, and addition appropriately lines up with addition. So the the fundamental things that make you a vector space, scaling and adding, this mapping is respecting them. Well, in addition to the scaling and the adding and the various properties they have, the axioms of vector space are also guaranteeing the existence of certain things. They guarantee the existence of an additive identity, and here we see a linear mapping has to send the additive identity to the additive identity. And furthermore, we know that in addition to the additive identity having to exist, we also know that additive inverses have to exist, and linear mappings have to respect those as well. So, linear mappings respect the fundamental operations of vector spaces, the scaling and the adding, and the other axioms that guarantee the existence of things, the additive identity and the additive inverses, linear mappings have to respect those as well. So, a linear mapping has to send 0 to 0, and a linear mapping has to send negatives to negatives. All right, and there are a couple of ways of proving these results. Let's talk about them. In fact, there are two methods of attack for both of these, and I'll go for both of them. All right, so method one for proving that the additive identity goes to the additive identity. So no, being a linear mapping means that you respect scaling and you respect adding. Well, the additive identity is the additive identity. And since we know addition is being respected, maybe I can pull something to make that work. Well, what do we remember about the additive identity? Well, adding it doesn't do anything. So, if I look at what t of the additive identity needs to be equal to, well, I can always sneak in a plus 0. There's always a phantom plus 0. No matter what vector space equation you have, you can always say, well, there's plus 0 hanging out in the end. In fact, there's plus as many zeros as you want, depending on whatever you're doing. All right, but linear respects addition, so the sums break up, and there we go. Cancellation lets us delete a t of 0 sub v from both sides. And so the additive identity goes to the additive identity. All right, so there we go. We've used the fact that the linear mapping respects addition. Now note, if you only knew your mapping respected addition, and we're going to talk about that in a moment, you would automatically get this. Right? You don't need the scaling to prove this. If you have addition, good. Likewise, you don't need addition to prove this. You can prove this by just the scaling. Now that one's a little sneakier, but we've kind of already talked about this trick. If you have the additive identity, you have scaling by 0. And so another, let me new page it. So another route of attack would be to note that the additive identity is really 0 scaling the additive identity, and I can pull 0 out, and we know scaling by 0 gets you the additive identity. Now, that one is really cheap, right? This is, we've talked about this one before when we were talking about subspaces. This is a real cheap move. But it works. All right, cool. Right, so note, method one is a bit more of the natural method of attack. But the scaling also works too, so if you wanted to do that way. And then similarly, for proving that inverses go to inverses, there's a similar sort of setup, where we can get it with just the addition, but we can also get it with just the scaling. Now with this one, just the scaling seems to be the obvious approach, because what do we know? Well, we know something about negatives in a vector space. They are really scaling by -1. And since I respect scaling, that means I can pull out scaling by -1 and get that negatives work. Like that. So method one here is kind of the more natural one, because, again, our brains are kind of hardwired to see, ooh, negatives. That really means scaling by -1. Right, that's always a trick we pull when we're, like, working with an equation, and you're like, oh, I got a minus, well, I really have multiplied by -1, so let me work with that. All right. Method 2 now will be relying on the additivity, but it will also rely on point 1. Because I'm going to use the additivity, but I'm also going to use point 1. And how does that go down? Well, I now know that 0 gets mapped to 0. So we can start off with that. But what we know about 0? Well, 0 is really x minus x. Okay, and then we remember that when we write x minus x, that's actually just shorthand for saying x plus -x. Because, again, there is no such thing as subtraction. There is adding by inverses. Subtraction is a lie. So is division. All right. And, hey, we have got a linear mapping, which means sums are respected. So that breaks apart like that. And, all right, t of x plus t of -x is equal to the additive identity. We proved that inverses are unique, so it has to be that t of -x is in fact equal to -t of x. Because adding it to t of x gets you the identity, and negative t of x is the unique element with that property. Cool. All right, so equipped with this, we now know that if you've got a linear mapping, it has to send 0 to 0. So this is also referred to as origin preserving. So it has to fix the origin. It also has to send negatives to negatives, and we have a name for that. What do we call a mapping that does that? From calculus, what is this called? Or pre-calc, whenever you learned this. If you can pull a minus sign out, what does that mean? Odd, right. Yeah, there you go. Even is if minus signs are canceled out. Odd is minus signs get pulled out. Right, so for example, cosine is even, because cosine of -x is cosine of x. Sine is odd, sine of -x is negative sine of x. Sine is not linear, but it is odd. All right, so here we see linear mappings have to send 0 to 0. They also have to be odd. So if you want to immediately ruin linearity, create a function that isn't odd. So as a consequence, of this, it's pretty easy to concoct nonlinear mappings. All right, so for example, the function x plus 1, out the window. This sends 0 to 1, not linear. Cosine, as we just mentioned, is not odd. So boom, out the window. Right, and for a more sophisticated mapping, let's say we got a function that's going to take elements out of R2 and send them to R2. And let's say it does the following. It squares x and deletes y. Right. This is also not linear. It does send 0 to 0, certainly. However, it can't pull out minus signs because the minus signs are going to get squared and be deleted. All right. Nice. So, with these two quick checks, it's pretty easy to create linear mappings that just aren't linear. What the fuck was that sentence I just said? It's pretty easy to create functions that are not linear, right? Just don't send 0 to 0 and don't respect subtraction. So it's pretty easy to create nonlinear things. So being linear, in some sense, is a little restrictive. There are some hard requirements on it. But what's very nice is that linear mappings are sort of naturally occurring. Differentiation is linear, integration is linear, transposing is linear, matrix multiplication is linear, dot products are linear. So a lot of things we care about and have deeply entrenched ourselves in are in fact linear. So that's quite nice. So we're going to study further properties of linear mappings. But before we do that, and that will be the next class, I want to take the time now, the last 10 minutes we have, to address an interesting problem. Okay, so I've got a wide question. Do we need both hypotheses for linearity? So if we go back to our definition for linearity, there were two requirements. Scalars are pulled out, and summations break apart. Now, as we've mentioned, whenever you set up a set of axioms for things, one thing you're interested in is minimal axioms. So, do I really need all of these? We said that for our definition of vector spaces, we have 8 axioms, and it turns out the existence of the additive identity and the existence of inverses, you can actually collapse that down into one axiom, right? And some people take this to an absolute extreme. There are things called Boolean algebras, and the people that study that figured out how to explain a Boolean algebra in one axiom. And we will talk about, you actually can combine these two into one. We kind of already saw that with subspaces. Subspaces respected scaling and adding, but we noted that you can do them simultaneously. But I'm asking something a little bit different. Let's focus on addition for a moment, and actually let's really think about what addition is doing. So let's go back to my question here. Do we need both hypotheses for linearity? By an nth additive function, we're going to mean a mapping from a vector space to a vector space that just respects the addition. So when we say additive, we mean we're only assuming that sums are respected. Okay, so if you have an additive mapping, cool. All right. Now it's worth noting if you wanted to know, well, what is just pulling out scalars? Those are usually referred to as homogeneous mappings. That one is a little less common. And some people would also argue, well, you're saying homogeneous of order 1. We don't need to get into that. But additive is pretty universal. Now, note something about additive mappings. There are some scalars I can immediately tell you that additive mappings have to pull out. All right, so we're going to not do a formal proof here, but kind of do kind of a quick, a pretty basic explanation of that some scalars are pretty easily seen to pull out. So for example, by the definition, it's pretty easy to see that I can pull 2 out. Well, because we know 2 scaling x is really 1 plus 1 scaling x, and then x distributes, and then it's x plus x. All right. And it's pretty obvious to see that you can extrapolate this and get all of the positive integers. Note 1 is for free, because scaling by 1 in a vector space doesn't do anything. All right, but 2, 3, 4, you can use a formal induction argument to show these have to work. All right, so all the positives have to go out. And likewise, as we noted in our proof, you only need the additivity to show that the additive identity maps to the additive identity. So if you're an additive mapping, you know you're going to send 0 to 0, and that secretly means you can pull out the 0 scalar, as seen there. All right, so I can pull out 0, I can pull out 1, I can pull out 2, so on and so forth. What about -1? Well, by a similar logic, we saw in the proof that negatives can be pulled out of an additive mapping alone. In the proof, we only use the additivity. So, hey, I know I can pull out all positive integers. I now know I can pull out 0, and I can pull out -1. And the previous points then would ensure that you can pull out any integer. Right, so we proved that all positive numbers get pulled out, we proved that you can pull out 0, and we proved that you can pull out -1. All right, well then you can pull out -2, because you can pull out -1 and then pull out 2. Then you can pull out -3, because you can pull out the minus and then pull out the 3. So on and so forth. So integers can always get pulled out. So if I only assume additive, integer scaling can be pulled out. And it gets better. Take a rational number. Okay. So again, let's recall my opinion on these things. By a rational number, I mean an integer over a positive integer. So I mean an integer over a natural number. Again, because I have the correct opinion that the natural numbers start at 1. All right, well, let's say I wanted to try to pull out rationals. Am I able to do that? And the answer is a big ol' yes. Now why? So at first glance, that might seem like, oh, wait, how can you pull that one off? Right, well, let's pull a little sneaky. Let's look at n scaling t of q. Right, well, I can pull that n in, right, because n is a positive, so that can go in, no problem. And what happens, what's n times q? Well, it's m. And what do we know about m? M is an integer, and I know I can pull out integers. Hey, there you go. Divide the n over, and we're done. So we've now verified that if you are additive, you can pull out every rational scalar. So just from additivity and some pretty basic maneuvering here, we can get all positive integers, then we can get all integers, and then you get all rational numbers can be pulled out. And as we know, the rational numbers are dense within the reals, in the sense that given any two real numbers, there's a rational number between them. Right? Rational numbers can approximate real numbers. Every real number is just a sequence of rational numbers. So this then raises a pretty exciting question. Well, wait a minute. I've just verified up to rationals get pulled out just from addition. But hopefully somewhere in our heads we go, well, wait a minute. The jump from rationals to reals is kind of big. Right? It's really big. The rational numbers are countable. The real numbers are not. Right? There is a fundamental gap between these two structures. Even though they have adding and multiplying and order theoretic things that line up, there is a huge difference between the two. So this led to the following pretty exciting question, and in particular, this is now generally known as Cauchy's functional equation. So hey, our boy Cauchy's back. Pretty natural question. When does additivity give linearity? So if I have an additive mapping, when do I know I can make the jump to a linear one? Additivity on its own guarantees that you can get rationals out. So anything further. So Cauchy, in particular, Cauchy did this for the real numbers. So Cauchy initially looked at additive mappings from the reals to the reals, and he wanted to know when can I pull out real scalars. He verified this part of it, where he went, oh, rationals can get pulled out, and then Cauchy being Cauchy went, oh, well, then if you assume continuity, then you can get all the real numbers out. All right, we're done. And so he just said, hey, we're finished, because everything's continuous to this dude. And further assumed continuity. And as we noted, when we talked about bases for vector spaces, we talked about, oh, these are sometimes called Hamel bases, because Hamel is the one who came through and demonstrated that you can actually construct discontinuous additive mappings from the reals to the reals. So additivity in general will not give you linearity. You can get pulling out rational scalars, but there are some mappings where you can't pull it out. And furthermore, that would ensure that it could not be linear. So if you are continuous and additive, you have to be linear. Cauchy figured that out. So if you constructed a discontinuous and additive, it turns out that you can't be linear, because if you were linear, then it can actually show you actually do have continuity. So, and there you go. Let me rephrase that. So non-linear additive, and thus they are discontinuous. That's a better way of phrasing it. All right, and the interesting thing about this is that Hamel did this by showing that the vector space R has a basis with respect to the rationals. So note, we proved every vector space has a basis with the assumption that the scalars we're working with are the reals, but as we noted, you can work with other scalars, and Hamel was the one who went, oh, by the way, wait, you can get bases for any scalar. It didn't matter which scalar you used. Pretty cool. So, indeed, if you're studying linearity, you need both hypotheses, additive and scalars. Neat stuff. So, some good history there. So if you want to dig into that a little bit deeper, check it out. Some fun stuff. And touching on a couple of crusty old dudes we've already talked about, Cauchy and Hamel. All right, and with that, that is the story for today. I'll see you next time.